Very good morning to everyone. It's a beautiful Friday morning, last day of the event. So I'm happy to see this crowd still attending Multicast in data center. So my name is Nagendra Kumar Nainar. I'm a senior technical leader with Cisco Services. I'm part of technical services, providing escalation support to customers like you. My day-to-day responsibilities includes, primarily providing escalation support in technologies like, the basic routing, multicast, MPLS. So that also includes, working on different platforms, including the Nexus platforms that we'll be looking into today. So about me, I have close to, 85 patents filed with different technologies. I've co-authored different, white papers and also standards in IETF. So yeah, that's it. I'd like to acknowledge these gentlemen here. They helped me with this content and also reviewing the content. I also borrowed some of the contents, from these gentlemen. So Matt Isa, he's a technical leader with, our engineering team. Richard Furr, he's my colleague and a good friend. And Alexandro, he's another colleague and a good friend of mine. This gentleman helped me with the content preparation. So this would be our agenda for today's presentation. So we'll start with, just giving a gist about the evolution of data center network. We'll then look into, the different multicast components related to the data center switches. We'll look into the control plane and the forwarding semantic about, how they work in, the data center switches. And then we'll look into some of the troubleshooting components. So this slide talks about, the evolution of data center network, starting from the traditional or the classical spanning tree-based network to, the latest or the modern network that we see in the current data center. So I'm sure you might be aware, the traditional data centers or the traditional, classical Ethernet, they use a spanning tree as a control plane protocol to build a loop-free layer 2 topology. So, the nature of spanning tree is more in a way that it chooses a set of or elects a set of links in forwarding state and another set of link in the blocking state. So as you could imagine, this is not a very efficient way of utilizing, the link within the network or the bandwidth within the network. Of course, there are quite a few enhancements in terms of, the PVST, the per VLAN spanning tree or the multi-spanning tree where, the same link will be positioned as blocking for one VLAN, wherein, forwarding for other VLAN. So this way we'll be still able to, it's not something like, one of the link will be completely unutilized. Rather, it's more like, load sharing for different VLAN. Still we'll be able to build a loop-free topology. But of course, as the network grows larger and larger, it becomes more and more complex, from an operational or a troubleshooting point of view. In order to address some of the challenges with network resiliency and high availability without compromising with the link utilization or the bandwidth utilization within the network, VPC was introduced. So VPC is a very successful feature. It's been deployed in most of the data center. So VPC is a virtual port channel where we'll have different member links from the downstream switch terminating on different chassis which are part of the same port channel. So the VPCs, or we call these chassis as VPC peers, so they'll be having a peer link over which they'll be able to synchronize different state entries and provide a loop-free topology still without having one of the member link in blocking state. So then comes fabric path. So far we used spanning tree, be it VPC based topology or the traditional classical topology. We still use spanning tree as a control plane protocol to build a loop-free topology. Wherein with fabric path, ISIS was extended further to use as a control plane for layer 2 topology. So ISIS was traditionally meant for CLNS, then it was extended for IP. With fabric path, it was further extended for layer 2. So with fabric path, the ISIS has two prime responsibility. The first one is to build a loop-free point-to-point and point-to-multipoint tunnels between or paths between different edge devices, fabric edge devices, and it also is used to advertise, the different MAC learned between, the edge devices. But to address the scalability issues related to fabric path and BGP was introduced. So here the the control plane will be BGP, wherein the data plane will be fabric path. So in the recent past, I'm sure you would have heard different buzzwords, including the multi-tenancy. So multi-tenancy is nothing but providing services to more than one customer. So using the same facility or the network to provide connectivity or any other services to more than one customers. So in a multi-tenant environment, or even in a very large-scale network, large-scale data center, the MSDC, it's not practically possible to keep building a very large network in order to provide a service to different customers. So with multi-tenancy, we need to provide data integrity and privacy. So it's practically not possible to build a very large network so that each of the tenant can have their own dedicated network. So in order to address this issue, why not use our existing IP network or the underlying network as a fabric and provide an overlay service, the layer 2 connectivity as an overlay service. So that's where VXLAN comes into picture. So the VXLAN is a MAC in IP protocol. So this is an encapsulation, this is a new encapsulation protocol where the edge devices, when it receives the layer 2 frame, it encapsulates with a new encapsulation header, overlay encapsulation header called VXLAN, which carries sufficient information about different tenants. And the VXLAN header in turn will be encapsulated with, of course, UDP and then IP address. So this way we'll be able to IP switch the layer 2 fabric over our IP underlay network. So traditionally, the VXLAN uses, the flood and learn mechanism, which is the one that was used by, the classical Ethernet. So basically, when the VTEP, we call it as VTEP, which is the VXLAN termination endpoint. So when it receives the VXLAN encapsulated layer 2 frame, we use the source MAC of the inner frame and the source IP address of the outer header to identify who's the remote VTEP to which I need to forward the traffic to if I want to send a frame destinated to this particular MAC address. So with this flood and prone, again, there are quite a few challenges in terms of scalability. So that's where BGP comes into picture. So BGP was extended further to advertise the MAC address and other, the VNI, the tunnel-related information. So BGP will be used as the control plane, and the VXLAN will be used as the data plane, and this is called Ethernet VPN. So right now, Ethernet VPN uses VXLAN as the only, or the Nexus switches, they support VXLAN as the data plane encapsulation model. But in future, probably we might be seeing other encapsulations like segment routing, MPLS. How many of you are aware of segment routing? Okay. So probably, segment routing, MPLS, or even SRv6 probably would be, supported in the future. So this is a view about the network evolution from a different dimension, from the topology or the designs point of view. So traditionally, who is actually handling layer 2 switches or layer 2 network for quite some time would have noticed that initially we had 3-tier model. So most of the layer 2 networks were designed with 3-tier model. We'll have access, aggregation, and core. But in the modern network, in order to reduce, the server to server latency, and also to, reduce the complexity and have a simple topology, most of the networks are designed with a 2-tier model, where we'll have leaf and spine. So the leaf layer switches would be the one that will be, connected to either the L2 sides or the server forms, and the spine would be the one that basically provides connectivity between the leaf switches. So as you could imagine, the leaf switches, from a platform positioning point of view, the leaf switches are expected to be more rich in features because that would be the one that provides different services. Wherein the spine switches, they are expected to be more powerful in terms of throughput and also packet processing, because the ultimate goal of the spine switches is to provide connectivity between different leaf switches. In a multi-tenant or a multi-pod environment, it still is possible to see a 3-tier model where in each of the pods we'll have leaf and spine, and each of these pods will be connected through a super spine. So, you'll have a leaf and then spine and a super spine. So still, in some of the very large data center, you could see the 3-tier model. So this is a view about the multi-tenant data center. So like I mentioned, in a multi-tenant data center, or wherever the VXLAN comes into picture, we'll have an IP fabric. So the IP network will be used as an underlay network, which could be completely enabled with IP or MPLS or IPv6. So this would be used as an underlay network. Sorry, So this will be used as the underlay network, and we'll have the edge devices providing the overlay service. The VTEPs are the one, like I said, the edge devices which basically will be doing all those encapsulation and decapsulation. So when we receive the layer 2 frame from the directly connected site, this would be the node that basically encapsulate with the VXLAN header and forward or IP switch the frames over the underlay network. So in our presentation, we actually will be looking into two elements. One is the data center, and the other one is multicast. So basically, our presentation is about how multicast works in data center. So before jumping into why and how multicast works in data center, let's pause for a minute and see what is multicast. So I probably assume that most of you are aware of the basics of multicast. So just to spruce up our knowledge, the need for multicast. There are quite a few applications which basically are required to send the traffic to more than one receivers. So one obvious way is to just unicast the traffic to each of those receivers. I mean, it's more obvious to see the servers creating different point-to-point sessions with different receivers, and they keep pumping the traffic to each of those receivers. But depending on the number of receivers, as the receivers grow larger and larger, it will have a direct hit on the application server's performance. Because one, it needs to create a lot of state entries to maintain who's it actually talking to, and it also need to replicate multiple copies and keep forwarding it to different receivers. It has to do all sort of packet processing like encapsulation, putting a different destination address, and then performing a lookup and then forward the traffic towards different egress interfaces. So it's not just the end applications server that actually have some performance issue. Even from a network's point of view, if you look into it, it's not a very efficient way, because any node or link will have more than one copy of the same data, except that it will be sent to different receivers. So this might cause congestions or packet losses. So that's where multicast comes into picture. So multicast is a one-to-many communication model. So it's somewhere between the unicast and the broadcast. So unicast is like one-to-one, and broadcast is like one-to-all. So this one is like one-to-many based communication model, where the end server will send just one copy of the data, and the packet will get replicated at the relevant branching points. So if there is a node which has different receivers reachable through a different interface, the node acts as a branching point, replicates the packet, and forward one copy to each of those egress interfaces. So from a server's point of view, if you look into it, it's just going to send one copy of it, irrespective of the number of receivers. And from the network elements point of view, none of the link will receive more than one copy of the same data stream. So the node, like I said, if there are different receivers which will be reachable through different egress interfaces, that acts as a branching point, replicate, and then forward it out. So another important use case, or something that got benefited with multicast, is the dynamic discovery protocols. Most of our protocols, the IGP protocols or any other protocols that requires dynamic way of discovering the other neighbors within the network, multicast is a very good option to do that. Why? Let's imagine you have a large network with, say, 100 or 500 devices, and out of which there are maybe 5 or 6 devices which are enabled with a specific feature. Let's go with an example of OSPF. Are you aware of OSPF? Okay. So in this case, if we were to go with another mechanism like a broadcast, so all these 100 or thousands of the devices will receive the broadcast message. They decapsulate the MAC address, MAC header, they look into the IP, and then they decapsulate and perform a lookup in the payload, and then realize, okay, this packet is not for me, and drop the packet. So this is not very efficient. Rather, with multicast, I hope you'll be aware that for each multicast, there will be a multicast MAC address. For multicast IP, there will be a multicast MAC address derived. So any of the nodes that are not enabled with the features, they won't even listen to those multicast MAC address. So when they receive a multicast MAC address for OSPF 010005E000005, they won't even listen to this. So at the layer 2 level, the packet will be dropped. It won't even decapsulate, perform a lookup in the IP address. So this is a very efficient way of utilizing the use cases like the dynamic way of discovering other neighbors in the network. So these are some of the components. Some are key components and some are optimization components. So the key components are required to have the multicast work, wherein The optimization components are more optional, which is mostly used for fine-tuning, the performance of fine-tuning the behavior of multicast. So we'll look into each of those components and how it basically works in the Nexus switches. Now, let's put those pieces together. Why multicast in data center? So data center is basically the facility which consolidates different application or the computing and the storage resources. So it makes more sense, or it's very obvious that you'll see a lot of those applications which basically leverages multicast, those residing within the data center. It either could be the server or it could be the receiver. For example, the servers, application servers like a video conferencing unit or media conferencing unit, which basically leverages multicast. The server could be residing within the data center. Or in case of data caching or data synchronization between different servers, the receiver in itself could be residing within the data center. So it's pretty common to see the nodes within the data center acting both as a server, which is like sending the multicast stream, or as receiver, which basically is like receiving the multicast stream. Now, it's not just the end application actually, which basically can leverage with the multicast. So even in multi-tenant data center, we saw that multi-tenants, the VXLAN is more like providing layer 2 service over IP fabric. So that the primary intention is to connect all those different layer 2 sites over a IP fabric. Now imagine you have a bump traffic, the broadcast unknown unicast or the multicast traffic. A good example is a ARP query. So when one of the ARP requests is originated from one layer 2 site, it needs to be delivered to all other sites, so that whoever is the owner of the IP address will be able to respond back with the ARP reply. But in order to do this, one option is when the VTAP, which is connected to the L2 site, which actually is originating the ARP request, it can replicate the packet and unicast it to different VTAPs. And this is actually possible. This is a feature called ingress replication. So if the remote VTAP, if the number of remote VTAPs is very less, we could go with this feature, which is ingress replication. The other option, or simple option, is to go with multicast. If you have a lot of remote VTAPs, if the tenant have multiple layer 2 connections, like 500s, it's not a wise decision to have ingress replication. Rather, it's better to go with multicast. So in this case, we'll have multicast, point to multi-point tunnels created between different VTAPs. So when the VTAP receives a bump traffic, again, the broadcast unknown unicast or the multicast traffic, it uses this multicast P2MP tunnel, encapsulate with VXLAN header, encapsulate with the multicast address, and flood it to all other remote VTAPs. So the remote VTAPs, they receive it, they decapsulate, they forward it to the connected L2 sites. So this is a quick view about the multicast protocols in data center. So IGMP is a protocol which basically is used by the receivers to signal or express their interest to receive the data stream. So in most of the data center or even the Nexus switches, it supports excuse me, the IGMP protocol. And these are some of the commonly seen protocols in a data center. And there are other protocols available which not all the Nexus switches actually supports it. In case of inter-data center or even for redundancy purpose, for rendezvous point, of course we'll be looking into it. It still is possible to have other additional protocols like MSGP. So let's now look into the Nexus multicast architecture. So you probably, are you familiar with NXOS? Okay, so I'm sure you probably would have noticed Nexus OS is a very modular architecture. Unlike the iOS, where all the software components will be loaded always, Nexus OS, it loads the components, software components as and when required. So you probably might be aware of something called feature command. So the feature command is required to enable certain features so that the relevant software components will be enabled, so you further can be configured and use those features. So it makes it very modular, which further allows to improve the performance or even the scalability. The multicast component, the Nexus OS multicast component is also modular in nature. IGMP is always enabled, but in order to configure PIM and use PIM as your multicast protocol, you again need to enable it. So feature PIM is required in order to have PIM enabled, PIM components loaded on the Nexus switches. Multicast in Nexus OS is VRF aware, so some of the platforms like Nexus 7K also supports Multicast VPN, which is providing multicast service for multi-tenant customers or VRF customers. Some of the multicast features are tweaked slightly in Nexus OS to accommodate different unique scenarios that are specific to data center. Like for example, VPC. We'll be heavily looking into how IGMP and PIM works in VPC environment, because like I said, VPC is one of the commonly seen feature and a very successful feature that's commonly seen in data centers. So one important thing here to notice, Nexus OS does not support PIM dense mode. PIM dense mode. Any guess about how it works? Yeah, flood and prune, yes. So it's not a very efficient way. I mean, it makes sense not to support this in a large data center because dense mode, like our friend said, flood and prune. I flood it over all my PIM-enabled interface, and I leave the responsibility to the downstream switch to say, hey, if you don't need the stream, just let me know so that I can stop sending it. So till that, we flood it over all the PIM-enabled interfaces. So in a large environment like a data center, it definitely doesn't make any sense to use PIM dense mode. And even it's not just data center, even in my experience, I've not seen, a PIM dense mode deployed in other non-data center related environments. So it makes sense, Nexus OS doesn't want to put too much effort in developing something that may not be, supported in data center, that will not be implemented in data center. So these are the components, MRIB, MFDM, and then we have different components in line card. So Nexus OS, of course, is a combination of the supervisor and also different line cards. So there are different components that resides within the supervisor or within the line card, which altogether will be helping to create different control plane state entries and also the forwarding plane state entries, which together will help with packet forwarding. So we'll look into each of those components. So the first one is MRIB, the multicast routing information base. So this is the component which basically creates the software multicast routing table. This component resides within the supervisor. So when you execute show IP mroute, whatever the start G and the SG entries that you basically look into, or the outputs that you get, that's fetched from this multicast RIB or the MRIB component. So it also helps with traffic statistics. When you execute show IP mroute, you'll be able to see the number of packets forwarded, number of packets dropped for each of those start G or the SG, which basically will be helped by this component. The next component is MFib. So this is the component that resides in line card. So this is the multicast routing table which resides within the line card. So again, this MFib is not the component that is used to use for packet forwarding. Rather, this is the component that resides within the line card that will be used to program the ASICs, which in turn will be used for packet forwarding. MFWD or multicast forward, this is another important component that resides within the supervisor. This is responsible for creating SG state entries. So if there is a switch which is directly connected to the source, when it receives the data traffic, it's this component's responsibility to create SG state entries and also to register the source with the rendezvous point. And from switch which is connected to the receiver's point of view, this component is responsible to create SG state entry when we receive a data stream on the shared tree. So there are different trees like shared tree and the shortest tree. So when we receive a traffic on a shared tree, we create a state entry SG and then build the shortest tree. So this is the component that is responsible to create those state entries. MFDM, this is a component that basically sits between the MRIB in supervisor and the MFib in the line card. So this is a component that gets all the state entries created from the MRIB, digested into something that can be understood by the MFib, because depending on different line cards. There are other components which changes depending on either the platform or depending on what features you basically have. So M2RIB is a component that primarily could be seen in Nexus 9K platforms, which is used for creating or populating the layer 2 multicast routing table, the multicast MAC forwarding table. The IPFib and L2 multicast are specific to 7000 Nexus 7K. So IPFib is more like MFib, but this is for the Nexus 7K. So this is the component that again resides in the IO module or the line card of Nexus 7K, which will be programming the hardware or the ASICs for packet forwarding. Okay, so let's now look into the protocols. So from an IGMP point of view, I'm sure probably you might be aware. So IGMP is a protocol which basically is used by the receivers to signal or to express their interest to receive the multicast stream. So there are different type of messages. So IGMP message used by the receivers to express the signal is called V2 membership report. So we send a membership report saying, okay, I'm interested to receive this group, or in case of SSM, we'll be using version 3, which says, okay, for this group from this source, I'm interested to receive the data traffic. So from a Nexus switcher's point of view, there's not much different from the basic IGMP's behavior. When you enable PIM and a IGMP, if it is a layer 3, it acts as a querier, and whenever it receives the join, it will be tracking. So all this functionality is pretty much similar to how it works in the traditional devices like iOS or other devices. IGMP snooping. So one important difference to note here is, of course, IGMP snooping is enabled by default on all the Nexus switches, but unlike the traditional switches, IGMP snooping is basically done based on IP and not MAC. So IGMP snooping and forwarding is actually based on IP address, though it is at layer 2. Can anyone guess why? Why do we need this? Okay, so yeah, so basically, traditionally, when we do the forwarding based on the MAC address, the way the MAC address, the multicast MAC address is derived from the IP addresses, the last 23 bits of the IP address will be concatenated to the well-known prefix for multicast MAC, which is 0100 5E00. So this way, imagine if there are like two streams, which is 226.0010 and 227.0010, they both will have the same multicast MAC address derived, 0100 5E0010. So this would be the MAC address that is used for both 226.0010 and 227.0010. So when the snooping and the forwarding is actually happening at the MAC layer, the MAC layer level, it is possible that the receivers might be receiving unintended traffic because of this overlapping multicast MAC. So this is what was addressed by the enhancement here, which basically is based on IP address. So if you look into the internal, the system internal outputs of the Nexus and the line cards, we could see that the snooping and the forwarding table will be populated with IP address as well. So though it is a layer 2 switch, they basically perform a lookup in the IP address. So each of those ports associated will be assigned, associated to the IP address. So when a packet is received at layer 2, it still will perform a lookup at IP address and then flood it to the right ports. So one thing, there is a CLI knob to basically toggle this behavior. So if you go under VLAN configuration, the VLAN number, there is a way to change this MAC lookup. It should be either IP-based lookup or MAC-based lookup. So honestly, I don't see any reason why you should fall back to the MAC-based lookup. But if for one other reason you really need to do it, then at least be very careful about those overlapping ones. So when you design your multicast, make sure that at least you could reduce the overlapping address as much as possible. Because for simplicity, you can simply say, okay, I'm going to have 100 or let's say 10, for example, groups. So for simplicity, you can simply say, okay, 226.001, 227.001, 228.001. It's more simple, but if you look from the forwarding's point of view, they all will end up with one MAC address. And particularly, if you have it overlapping with one of the well-known addresses like the IGMP, MAC addresses, then that will be more, it might be a chaos. So when you design the multicast addressing, consider this consider this to make sure that you don't end up with a lot of overlapping MAC addresses. IGMP in VPC environment. So like I said, VPC is one of the commonly deployed feature in in data center. So in this example, we have this VPC switches which are layer 2. So when they are layer 2, they simply receive IGMP, and they actually will not be processing the packet. They simply will be flooding it over the M router ports towards the multicast router. So the host is actually sending a IGMP join for any group start G, which the downstream switch, it's a traditional layer 2 switch. It could be a traditional layer 2 switch. So it just receive it, and based on the local ether hashing algorithm, it chooses one of the member port. Like I said, both the member ports will be forwarding. So it chooses one of the member port, and in this case, it chooses the one pointing towards switch 1. So it goes to switch 1. So when switch 1 receives it, at layer 2, like I said, IGMP snooping is enabled by default. So it snoops IGMP, it populates its local table, and it uses a message called CFS message, Cisco Fabric Service message, to synchronize the state information with switch 2. So at any point in time, both the VPC peers, they will have the same snooping table. So this is traditional layer 2. The VPC peer is actually layer 2, so any other IGMP processing will not be actually happening. Now, this is another example where the VPC peers, they are layer 3. So they not only snoop the IGMP, but they will also process it. So let's now look into how they basically works. So again, in this example, the host sends IGMP join. The downstream switch, it uses some local hashing algorithm to identify the ether channel. Again, it uses switch 1. Switch 1 receives it. So the first thing, it snoops the IGMP, populates its local IGMP table. It uses CFS message to exchange the synchronization. But in addition, it also forwards that IGMP over the peer link to the VPC peer. Why? Because we'll have PIM enabled, this peer link will be marked as M router port. So it's expected that we obviously will be forwarding through M router port. So switch 1 and switch 2 will not only have the same snooping table, but it also will have the start G entries created on the IGMP routing table, and also the MRIP table, which is nothing but our multicast routing table. So IGMP snooping in VXLAN environment. So IGMP snooping for traditional VLAN is always on, but for VXLAN it's optional. It's not on by default. So when you configure a Nexus switch as a VTEP, and if you have IGMP snooping enabled, by default the NV interface or the tunnel interface will always be included as a port and flood all the control plane and the data plane. Whatever the bump traffic will keep on flooding over the NV interface, which is the VTEP interface. So this is not an efficient way. So there is a command which was introduced from 703i5, primarily on Nexus 9K platforms. Because VTEP 9K is the primarily positioned VTEP platforms. So this is the command, IP IGMP snooping VXLAN. So this command basically does the snooping even on VXLAN interfaces. So whenever we receive any bump traffic or any other traffic from the VTEP or the VXLAN interface, it will perform the snooping and ensure that only the relevant control plane or the data plane traffic are getting flooded over the VTEP interfaces. So this way will help reduce the number of packets getting flooded over our IP fabric. So when we enable this component, we also need to enable some of the internal TCAMs for resource purpose. So in addition to this command, we also need to enable the TCAM 2564 with double wide, which basically triggers some of the internal resources to accommodate this feature. So Nexus switches also support static way of defining IGMP. So a couple of times, I've been asked by different customers saying, okay, why do we need, is there a benefit in configuring static IGMP? Why do we really need IGMP? So one, the common thing that always comes up in mind for static IGMP is, okay, the end application basically does not support IGMP. So to some extent, I would say it is true, because if you look into most of the current applications, they are not legacy. So most of those end applications basically support IGMP. But there are some of the applications which are like homegrown, at least with all these software-defined networking and the or technical prowess about developing our own applications in different customer environment, it still is possible that they might be coming up with some application which is good enough to process the packet and do all those things, fancy things from the payload. But they don't want to do a lot of work in developing the module about how can I receive the data traffic and then do the processing. So with the static IGMP, of course, we could eliminate this. On the switches, we can configure static IGMP to just forward the traffic. So this is one simple example. And the other one is, there are some applications which basically will be acting as a receiver always. So the moment when it comes up, it will be a receiver for a particular multicast. So in this case, it doesn't make any sense to always send the control plane saying, hey, I'm a receiver for this group. As long as, of course, the box is up and running, it is going to be a receiver. So in those cases, you could eliminate some of the control plane stuff by simply configuring the static IGMP. So the way to configure static IGMP, there are two different ways of configuring static IGMP. One is using the join group, and the other one is static OAF. So the difference between these two is, when you configure join group, it's basically like the packets get punted to the CPU. So this is used for testing purposes. If you want to ensure that your multicast tree is up and running, you could trigger multicast ping from your sender or the connected switch to see if all those receivers or the tree is built up to the receivers. So in order to do it, you need the last stop switches, whichever is connected to the receivers, to punt the packet to the CPU so that they can understand that, okay, this is a ping traffic and I need to respond back. So this is a simple way. But again, for production environment, this is definitely not supported. Because like I said, the packets get punted to CPU. It tries to software switch the packet. For production environment, it's better to use the static OAF, which basically is like programming your hardware ASICs. So static way, even though you don't receive any IGMP join, you still will be configuring, programming your hardware ASICs with the different outgoing interfaces based on what you configure here. So static IGMP, when we configure, we also need to enable the IGMP snooping, static IGMP snooping. Okay, so multicast routing protocols. There are different routing protocols which are supported in different platforms. PIM is the commonly deployed one in data center. So there are other protocols like multi-protocol BGP or BEER, which is right now not supported in data centers. So how many of you are aware of BEER? I was just talking to one of our friend here. Awesome. Okay, so BEER is a stateless multicast protocol. I mean, there are some discussions, but there is no roadmap or anything about the support on Nexus. But maybe in future we might be seeing this. But it's good to know about BEER. So we'll be focusing on the different PIM modes. Like I said, dense mode is not supported. ASM, SSM, and bidirectional, it's supported in Nexus switches. Okay, so any source multicast, this is nothing but our PIM sparse mode. So in this mode, we will be building shared tree and also the source tree. So rendezvous point is something that is very important in this mode. So the receivers, they use some out-of-band mechanism to get the group address, but they are not aware of the source. And the source, they are not aware of the receivers. So rendezvous point is the middleman who actually will be acting as the connecting point between the source and the receivers. So the receivers will actually be building the tree towards the rendezvous point. And the rendezvous point, of course, do nothing as long as it's not receiving any data traffic from the source. So once it starts receiving the stream, it uses our shared tree to forward the traffic. The receivers will, when they receive the data stream, they trigger a shortest tree, a better path towards the source, and start receiving the traffic. So Nexus switches also supports just relying or just sticking to the shared tree and not to go with the shortest tree. Any guess on what is the benefit if we just rely on the shared tree? State entries, yes. So if we just get stuck with or if we simply receive the traffic from the shared tree, it still will have one start irrespective of the number of sources. But if you create the shortest tree, we create a lot of state entries because for each of those sources, we'll create multiple SG state entries. But the while this is I won't say this is a downside, but the benefit with the shortest tree is we'll receive the traffic over an optimal path. So imagine you have a source which is connected to one of the switch, which is directly connected to the switch to the receiver, wherein the RP is sitting somewhere in the network. In this case, if you simply were to rely on the shared tree, so the traffic from the your source needs to go all the way up to the RP, and then from RP it needs to come to the receivers. Wherein with shared tree, shortest tree, it can build a shortest tree from the receiver to the source, and they can use the optimal path to receive the traffic. Source-specific multicast, they use out-of-band mechanism to not only the receivers use out-of-band mechanism to not only learn the group address, but also the source from where the stream is available. So because the receivers are already aware of the source and the group, there is no need for rendezvous point. So with PIM SPAS mode, SSM, the source-specific mode, we don't need rendezvous point at all. But otherwise, the way it builds the tree, it's almost similar to how we build the shortest tree in ASM. We just use the PIM join, towards the switch connected to the source. So the default range is 232.0.0.8, and if for one other reason you want to use a different range, then this is the command, PIM, IP PIM SSM range, and whatever the range that you want to use. Bidirectional mode, in a many-to-many environment, bidirectional mode is a very good option. So there are quite a few applications which not only where the endpoints will not only act as a receiver, but they also will be acting as a source. Like for example, the video conferencing unit. So all the endpoints, they not only receive the video stream from other endpoints, but they also will send their own video stream to other endpoints. So in this case, all the receivers can also act as a source. So bidirectional mode is a very good option for this. In this mode, we won't create SG state entries. We completely rely on start G, and a designated forwarder will be elected in a way that whenever we receive a traffic from any of, there is a concept called upstream and downstream. The upstream is towards the rendezvous point, and the downstream is towards the receivers. So when we receive a traffic from any of the upstream, any of the downstream, we will flood it through the downstream and also to the upstream, so that it reaches the rendezvous point. Wherein if we receive the traffic from upstream, we simply will be flooding it over the downstreams. So this way, we'll be able to flood the traffic without any SG state entries and without any loops. PIM in VPC environment. So PIM in VPC environment, a couple of things to note here is, in a VPC environment, in most of the platforms, any source multicast is supported. SSM or bidirectional is not supported. With Nexus 9K, in the recent images, any source multicast and also source specific, the SSM is also supported. But the way how it works is more similar to how we will be seeing it here. PIM neighborship can be established between the VPC peers, but PIM neighborship cannot be established with any node over the member link. So in this case, if you have it this way, you can't enable PIM here and try to have the PIM neighborship between these two boxes. So just for testing purpose, if you do it, you might probably see the neighborship coming up, but it's not officially supported, or it won't be able to send the PIM join because VPC doesn't maintain a lot of the PIM related state entries. VPC, so let's look into the register behavior. So in register behavior, the source is connected to our VPC peers. So in this case, the source would be sending some data traffic. So the source would be sending some data traffic which goes to one of the layer 2 switches. So the layer 2 switch, they receive the data traffic, and because of the M router, because the VPC peer link is marked as M router, they'll be flooding it over the peer link as well. So don't worry about this. We'll be looking into each of those show outputs in our forthcoming slides. So the data traffic from the source goes to the switch. No matter which link it uses, it goes to one of the switch, and through the peer link, it goes to the other switch as well. So from the first hop switch, or the switch which is connected to the source point of view, there are two responsibilities. Of course, like I said, the multicast forward component kicks in, it creates the SG state entry, and it also tries to register the source with the rendezvous point. So here, because they both are receiving, we need one of the guy to do this. So we follow the traditional layer 2 design, which is the classical design, which is like whoever is the PIM designated router would be the one that will register the source address with the rendezvous point. So in this case, we will be having the VPC, the PIM neighborship between these VPC peers. So whoever is the designated router would be the one that will register. The other one will do nothing with the source. It creates the state entries but does not do any registration. Join behavior. So this is an example where we have a receiver connected to the VPC peer. So receiver sends an IGMP join. So the switch, the downstream switch, takes a local decision. It forwards to one of the switch. So this is the traditional IGMP behavior that we saw. So this is no way different. So just to reiterate, they snoops both the VPC peers will snoop. They create the snooping table, and they also create a StarG state entry. So till here, everything is IGMP. Now, looking into the PIM's behavior, they both will be building the tree. So both VPC peers, they will send a PIM join and build the shared tree towards the rendezvous point. So both will build the tree, and they receive the data traffic. They receive the data traffic, and they both build the shared tree. They receive the data traffic, and when they receive the data traffic, they create this shortest tree and build the SG state entry and build the shortest tree. But here, one of the node will be forwarding. The other node will not be forwarding. So we use CFS message to identify one of the node as the active forwarder. Again, we'll look into the show commands and the event histories. But to give a gist about that, when both the nodes create the SG state entry, they will create the SG state entry here. They build the tree, and they start receiving the traffic. And by this time, they use the CFS message to exchange, to negotiate who should be the active forwarder. Whoever is the active forwarder will populate the outgoing interface list and keep flooding the traffic, wherein the other one will remove the outgoing interface list and will not forward the traffic. But it will not only forward the traffic, but it also will not keep sending the PIM join. So the downside with this approach is the moment when your active forwarder fails, there is a delay introduced because the non-active forwarder should learn that the node has failed, and it takes the responsibility of active forwarder. It has to build the tree towards the source and then start receiving the traffic and then flood it. So to address this, there is something called pre-built SPT. So pre-built SPT is a feature that is available. When you enable this, of course, you need to enable it on both the VPC peers. So when you enable this, both the VPC peers, they will not only build the shared tree, but also the shortest tree, and they keep receiving the traffic. But the active forwarder will forward the traffic, wherein the other one will keep dropping the packet. So this is the difference between pre-built and with and without this pre-built command. So the moment when the active forwarder fails, the non-active forwarder, it simply want to take the role and start sending the traffic. It doesn't have to build the traffic because it already is, and the tree is built and it already is receiving the traffic. Yes. Mm-hmm. Non-VPC. So you mean to say this is not a VPC environment? Okay. Okay. Yeah, in this case, yes, because in this case, you will receive the traffic and you will have those non-VPC related interface as your outgoing interface. So in that case, yes. So good example. So if in this case, with or without PIM pre-built SPT doesn't make any difference because it anyway has to receive the data stream so that it can forward the traffic towards the other L3 interface. But if the scenario is in a way that you just have one interface, which is a VPC egress interface, in that case, pre-built SPT comes into picture, and that's very handy here. Very good question. Thanks. So like we saw earlier, this basically is a trade-off. So the downside with pre-built SPT is, of course, you keep receiving the traffic all the way from the sources for different groups and keep dropping the packet. But the benefit with this approach is the moment when the active forwarder fails, you can immediately take over and start forwarding the traffic. So it's basically a trade-off between the bandwidth utilization in the network and the delay. It completely depends on your end application's requirement. So PIM underlay and overlay in VXLAN or any other multi-tenant environment, the underlay and the overlay, they're completely independent. So using PIM dense mode on PIM ASM on the underlay doesn't mean that PIM ASM should be enabled for the overlay as well. So currently SSM is not supported. SSM or even bidirectional is not supported for VXLAN environment. So ASM is the only mode that is supported on VXLAN. So in the forthcoming slides, we'll also see a configuration example and how it basically built the tree. So this is a configuration example for underlay multicast. So like I said earlier, feature PIM is mandatory because IGMP is enabled by default, but PIM is not. So Nexus OS, it requires feature command to enable different features so that you'll be able to configure different things. So without this command, you won't even see any of those PIM, IP PIM related commands at all. So this is the configuration about static way of defining the rendezvous point. Just go to different egress interfaces and enable the PIM whatever mode, spas mode or. So this is an example of overlay configuration. So I would specifically focus on this one. So this is the interface NVE or the VTEP interface where you configure this member VNI, the VNI name, and the multicast group. So one of the requirement is like each tenant or each VNI, of course, VNI specifies different tenants. So each VNI should have a unique multicast group address. So that's how they will be able to ensure that we deliver the bump traffic only to remote VTEPs who are actually having a directly connected site for this VNI. So rendezvous point, like I said, it plays a very key role in any source multicast. So it plays as a role of acting as a middleman between the source and the receivers. So it's not required or it doesn't have any role at all in PIM SSM. There are different ways of deploying a rendezvous point. Static or the dynamic, two ways of dynamically deploying. One is auto RP and the other one is BSR. All these modes are available in Nexus OS. Depending on the requirement, we might change this. Redundancy is one of the consideration for rendezvous point, and Anycast rendezvous point is also supported in Nexus switches. So this is a configuration example of a different way of deploying rendezvous point. So the first one is the static way of defining. So we simply will say IPPM RP address, and we could specify it based on a group or a prefix list or even a route map. Now, the downside, I'm sure you could imagine, is one, it requires a lot of configuration on different switches because all these switches should understand rendezvous point. So if it is a very large network, going and configuring it doesn't make any sense, or it's not practically possible. And the other downside with this approach is if in future you want to change the rendezvous point, it requires a lot of configuration changes again. So the simple other option is to use the dynamic way of deploying rendezvous point. So the other two options are relying on auto RP or BSR. One is like Cisco's proprietary and the other one is standard. So that's the only difference. Otherwise, there's not many difference with BSR and auto RP. Anycast RP, in case of load sharing or redundancy purpose, Anycast RP could be used. So Anycast RP is like having the same IP address configured on different devices. So again, going with the example of leaf and spine, it makes more sense to position the spine switches as your rendezvous point. So more than one switches will be configured with the very same IP address, and this IP address would be configured as the rendezvous point address on different leaf switches and of course the other switches. So let's go with one example. This is a pretty simple example about how to configure the Anycast. So on each of those switches, we'll go and configure Anycast RP, and we not only configure this. So 10.1.12.12 is the Anycast IP address, which would be the IP address that will be using in different RPs. And this is the actual unicast address to reach each of those RPs. So here in this example, 10.1.1.1 is the unicast address to reach switch 1, and 10.1.2.2 is the unicast address to reach switch 2. They both will be configured with 10.1.12.12, which is the Anycast RP. So this would be the address that will be configured on other devices as the RP address. Now let's imagine an example where this is a source and these two are receivers. So they obviously will be building the tree towards whoever is the closest address or who is the closest rendezvous point. So in this case, these two receivers, they build the tree towards 10.1.1.1 because this is the closest one. And if this source starts sending the data traffic, it basically goes to this switch. This switch does not know about any of these receivers. So in order to connect the receivers which are registered with or build the tree with a different rendezvous point, We basically use either MSDP or PIM between these two switches. So the moment when we enable Anycast, as you could see here, each of those Anycast RPs will also know the other RPs. So when you execute this show IP PIM RP on switch 1 or switch 2, they will have all these address configured, all these address listed. So the moment when there is an active source, a PIM register received, they either use MSDP or PIM register and forward that to all other switches. So they simply, yeah, go ahead.
Quick question. This configuration you need to build your underlay for VXLAN.
That's right, yes.
The same configuration and the same rendezvous points will be used to forward multicast traffic in the overlay?
You can use it. So they're completely independent. So the RP of underlay is not overlapping with the RP of the overlay. They completely will be having their own RPs. So the RP can't be reused for overlay. So the underlay RP will be using to provide the underlay multicast service, and you use this to provide the connectivity, overlay connectivity. So they are completely independent. So coming back to the rendezvous point, when any of the RP receives the register, it sends the PIM register or the MSDP source active message to other RP saying, okay, there is an active source. If any of you have receivers, just build your shortest tree and start receiving the traffic. Multicast load distribution. Load distribution is enabled by default. So load distribution is nothing but sharing the or leveraging our ECMP paths to different sources and receive the traffic from different interfaces. So imagine your rendezvous point or your source address is reachable through different egress interfaces, and if there are more than one groups that you want to receive from the source. Instead of just sticking with one interface and keep building the tree towards one interface and start flooding and overutilizing the link, this feature is more like distributing in a way that when I receive SG for SG1, I use one link, and when I receive SG2, I use another link. So there are different options basically that's available. When you use none, that's basically is disabling it. So it simply will stick with one of the interface. SG-based hashing, it's like, it uses the entropy based on the source and the destination, or the source and the group address. It uses some, local hashing to identify what should be the upstream interface, based on which it will be sending the PIM join towards the upstream interface. Resilience is more like to avoid reconvergence whenever there is any change. So imagine you have two ECMP paths, and suddenly if there is a new ECMP that was included. So the resiliency basically comes into picture, but you can disable it. But if the third one comes into, the ECMP paths to reach the source has become 3 from 2, without this resilience, it tried to reconvert. So it tried to see, can I, load share some of my existing flows over this new link. So in this case, it tried to build the path towards, the other existing, the new upstream interface. So without this, it tries to stick to whatever we have. So even though if a new, upstream interface comes up, it tries to load balance within the existing one, and when there is a new stream or when there is a new tree that comes up, then it tries to use the, new interfaces. BFD. So how many of you are using BFD in your network? Okay. So BFD is the continuity check protocol, which basically is a good protocol to use a rapid way of detecting the failures. So are you guys just using BFD or seamless BFD? Are you aware of seamless BFD? Okay. So Nexus OS supports BFD, and right now with PIM could be included or used as a BFD client. So it basically is used to detect any rapid failure of PIM neighbors, so that it will be able to either rebuild through other path, or it could take over and do other responsibilities like registering the source or forwarding the traffic. So the command is global. IPPIM BFD will enable BFD for all the PIM enabled interfaces, but this could also be disabled on a per interface basis. So it's a pretty simple command, but very powerful and useful. VDC, I would say there is not much consideration that is required from the Nexus OS multicast components. Just like any other control plane protocols, even the control plane, multicast control plane instances like PIM and IGMP, they are completely dedicated for each of the VDC instances. And again, just like any other features, the forwarding, they use the same infrastructure. So anything goofed up on the infrastructure might affect multicast as well. But otherwise, there's no other special consideration for multicast components. Control plane intervene. So control plane, whoever is actually handling Nexus switches probably will be aware. Control plane is enabled by default, and it comes up with a predefined set of values. In Nexus switches, there are different scenarios where we could see packets getting punted to CPU. So COP is basically to protect the CPU from unwanted traffic getting punted. So in some situation, you probably might need to tweak to accommodate your changes. So like by default, Nexus switches does not perform software switching, packet software switching. So that's why you see some issues when you start the data traffic initially till it build the shared tree, shortest tree, sorry. But you still could tweak the behavior to software replicate the packet, which might end up getting the packets getting punted to CPU. So if you still want to do those features, then we need to tweak the attributes to ensure that the packets are not, though you have software replicate command enabled. Of course, we have a slide talking about that, so don't worry. Though you have that command, the COP might come into picture and dropping the packet, so ultimately the receivers may not receive it. So like I said, if you have any specific reason to do that, then in a production, in a testing environment, it's better to test, tweak the attributes, and then move that values to the production environment. Okay, so let's now look into the control plane and the data plane semantic. Let's now look into the state entries and the packet forwarding. SPAS mode. So receiver sends an IGMP, so Nexus switch 3, switch 3, which simply will create some state entries. Okay, so this is an example which is without VPC, so this is a layer 3 switch. So this is just to spruce up our knowledge on how each of those state entries does. So when it receives, the first component that comes into a picture is our MRIP component, like I said, which is responsible to create the software multicast routing state entries. So the MRIP component will create a StarG with the relevant outgoing interface, and it also triggers the PIM joins. So the PIM join will be towards the rendezvous point, the shared tree. The rendezvous point creates a StarG entry and do nothing till it receives the data stream. Now, the data from S1 is received by switch 1. So the MFWD component kicks in here, which is responsible to create the SG state entry and also to register the source. So it creates a SG state entry and uses PIM register to register the source to switch 2. Switch 2 receives it, it creates SG state entry and flood the traffic. Now, switch 3, when it receives the data traffic over the shared tree, again, MFWD component comes into picture. It creates SG state entry and build the shortest tree towards Nexus switch 1, which is directly connected to switch, and start receiving the traffic. With SPAS mode, it's no way different, except that we don't have the shared tree. We don't need to build the tree towards the rendezvous point. Only difference is the protocol IGMP is supposed to be version 3. So version 2 basically carries only the group address and not the source address. With IGMP version 3, it carries both source address and also the group address. So when you enable PIM SSM, we need IGMP version 3 in the receivers. So again, it's the same. When it receives, the MFWD component will kick in to create the SG state entries and build the shortest tree towards switch 1, and it will receive the traffic. PIP bidirectional, it's almost similar to the ASM mode. Again, it's no way different. Like I said, there is no SG state entries created at all, so only we'll be seeing StarG state entries created on all these switches. So this is some of the examples with some show outputs. So here we have IGMP join. This is a VPC environment, and this is a layer 3 switch. So receiver sends IGMP join, switch 3 forwarded to Nexus switch 2. It creates start G. So Nexus switch 2, when it receives, it first creates a snooping table. It populates the snooping table, and then it creates the start G entry in IGMP table, and then populate the mrib. Then it exchanges the information using CFS to Nexus switch 1. So switch 1 creates the start G state entries. And then, like I said, they both will be building the PIM share tree towards the rendezvous point. So this is an output. So show IP mroute, excuse me. So show IP mroute, 233 or whatever group. As you could see, we created start G state entries, and both switch 1 and switch 2 will have the outgoing interface list populated from wherever we receive the IGMP join. Now, the moment when we start receiving data traffic, the first thing is MFWD component kicks in. It creates SG state entries and start building the tree towards the source. And in addition, it also uses CFS message to identify who should be the active winner. So this is an output. So the active forwarder will be decided based on the metric. So when I start building the shortest tree, I get both the VPC peers will basically use CFS message to exchange the metric to reach the source. So in this case, imagine the metric to reach source is 10 on switch 1 and 100 on switch 2. Then switch 1 wins because of the better metric. So because switch 1 become the active forwarder, you could see that switch 1 will have outgoing interface list populated, wherein switch 2 will not have it. So the outgoing interface list will be marked as 0. So now to answer your question, if there is another L3 interface, which is actually have an acting receiver, then it's expected to see it here. The count will not be 0. So this example is primarily from highlighting about how it basically forwards on the VPC. So this is the command, like I said earlier, the PIM pre-built SPT. So from an output point of view, you won't any difference between IP PIM pre-built and with and without PIM pre-built, because the outgoing interface will still be 0, except that it keeps sending. The state entries will be created and start receiving the traffic and drop the traffic at the non-active forwarder. So that's the only difference between PIM pre-built SPT with and without this command. Okay, so this is an example where we have the source connected to the VPC peers. So the data traffic, it goes to the switch. It takes a local decision and use this member link and forward the traffic. So like I said, at layer 2, when I receive the traffic, I obviously will be flooding it over the mrouter port. So it does the same thing here. So when switch 2 receive it, it creates SG state entry, and it also forward the data over the peer link. So the traffic will be received by both switch 1 and switch 2. They both will have SG state entries created. Now the one that will be registering the source with the rendezvous point is the PIM designated router for this VLAN. So in our example, switch 2 is the rendezvous point. So this would be the node that will be registering with rendezvous point. So this is an example when you have the data traffic flowing from the source. When you execute show IP mroute, you could see that the SG is created on both switch 1 and switch 2. The outgoing interface, of course, is 0 because there is no active join, either IGMP join or PIM join received from any of the interfaces. Now, the prime responsibility is to register this source with the rendezvous point. So this is a debug from the RP, which in this case is a different iOS. So as you could see, it receives the V2 register from 10.100.2, which is our switch 2. So this is the only node that will be registering or sending a PIM register to the rendezvous point. So VTUP or the VXLAN environment, the way it builds ASM, like I said, ASM is the only mode which is supported. The way it builds ASM is no way different from what we saw in the past. The only difference is it's configuration driven and not IGMP driven. So in the past, when I receive a IGMP, I create start G state entries and then I trigger a PIM join. Wherein in this case, it's configuration driven. So there is no PIM, of course, here. So this is the command. Like I was mentioning earlier, for each VNI, we need a unique multicast group address assigned. So this is the command for member VNI. We configure 232.1.1.1. So when you configure this, there'll be a start G entry created for this group, and it tries to build the tree towards the rendezvous point. Okay, let's look into some of the troubleshooting components. So I'm sure you probably might be aware of event history. Whoever is actually handling Nexus switches will be familiar with event histories. So event history is more like a inbuilt debug logs where the Nexus switches are capable of handling to a certain extent, which will be very handy when we need to perform some root cause analysis. So unlike the traditional old days where either the problem was fixed by themselves, or we shut and shut the interface and we fix the issue, and we run out of logs and we don't have an easy way to identify the root cause. So one way is to wait for a maintenance window, reproduce the issue, enable some debugs, collect those debugs, and then perform the analysis. So this is a inbuilt way where we could just rely on different event histories, which is very handy, which gives you a better understanding about the different communication between different components that we are looking into so far. So this is an example of the multicast forwarding event history. Like I said, this is the component which is responsible to create the SG state entries. As you could see here, it creates a state entry for this particular SNG. So by looking into this, we'll be able to see the different activities that was done by this particular component. This is another example where IGMP is creating a state entry in MRIB, or requesting the MRIB component to create a state entry. So the moment when we receive IGMP join, the first thing is to create a start G state entry in IGMP table, and once we create that, IGMP talks to MRIB component to create a start G entry. So as you could see here, the IGMP internal event history shows that we received a V2 membership report. And then if we look into the IGMP internal, we could also see that IGMP adds, and then it asks MRIB to create the start G entry for that particular group. So because we have these event histories, it doesn't mean that we don't have any debugs. Though it helps, the event histories helps us to get a lot of logs. There are still scenarios where we may need debug to have a better understanding with whatever is actually missing with the event histories. So Nexus switches basically allows creating a debug log file and diverting all the debug messages to one particular log file, which is very useful. So this is a command to create the log file. It basically creates a log file in the log directory, and then enable the set of debugs. And if you look into the show debug, we'll be able to see all the messages, or all the debug messages in the file. Another simple option is to use SCP or FTP to completely move the file to a centralized server for analysis. These are some of the show text and event histories, which will be very handy. This is a cheat sheet that we created, and some of our friends are even I use it during troubleshooting. So these are like on a per module basis, per component basis. For each component, we have different show texts or different event histories, which will help us understand the inter-component communication and also intra-component communication. So this is just a follow-up about different components. So if you are running short of time, so many times I'm sure you probably would have encountered, you know what is the workaround to fix this issue, but you don't want to fix this issue because you want to troubleshoot it further to identify why it caused this issue, so that you can avoid it happening again. So of course, we can rely on all the cheat sheets that I was showing in the previous slides. There are quite a few show commands and show events and show tags. So if you are running short of time, if it is a production network and a peak hours, and you don't want to take a lot of time, this is a simple cheat sheet, which of course does not guarantee that you will be able to root cause your problem, but it improves the chances, because most of these are a simplified version of different log and event histories which are consolidated together. Okay, so let's look into some of the troubleshooting, the commonly seen issues, and the different show commands or event histories that we could use to identify where the problem is. So in our tag world, some of the commonly seen issues, this is one of the commonly seen issues, where when the data traffic is started, some of the first packet is not excuse me, actually received by the receivers. So it's like, momentarily, for few moments or few seconds, the receivers are not actually receiving, and then everything is working fine. Why are we losing this packet for, few initial few seconds? So the answer is, like I said, we need the packet to get punted to CPU so that it can create different state entries. And when it happens, the packet is actually at the CPU level, or the packet is actually at the software. And Nexus by default does not software switch the packet. When I receive, different components kicks in. One good example is the Nexus switches has built the shared tree, and when it receives the data traffic, it needs to create the SG state entry. The MFWD component comes into picture. But in order to do it, when the packet gets punted to CPU, it creates a state entry, but it doesn't further forward it out. It simply will drop the packet. This basically is to help not overload the CPU. So this is an expected behavior. So if in production in your network, if you see this, this is the reason. So don't just be panic about either the server or the network. There is a command to toggle this behavior. So IP routing multicast software replicate is a command that's available, which toggles this behavior. But personally, I wouldn't recommend that because, like I mentioned, depending on the volume of the traffic or the number of streams, it might end up like, the CPU will be trying to do too many works to software switch the packet. There are other type of packets which probably get punted to CPU. From a first hop router's point of view or the switcher's point of view, which is connected to the source, when I start receiving the data traffic, the packet will be getting punted to CPU to create the SG state entry and to register with the rendezvous point, register the source with the rendezvous point. So in order to do this, the packet will get punted to CPU. Now from a rendezvous point's point of view, because it's a PIM unicast message, the register is a unicast message, so the packet will get punted to CPU to create the SG state entry and start building the shortest tree towards the source. And from the switch which are connected to the receiver's point of view, again, when it receives the data from the shared tree, it's expected to punt the packet to CPU so that it can create the SG state entries. So there are quite a few instances where the packet will get punted to CPU. In addition, it also includes other control plane protocols, like any of the PIM receive PIM messages or IGMP messages. All those messages are required to be processed by the CPU. So it's expected that the packet get punted to CPU. Now, how do we know that, or how can we see what are the type of packets that get punted to CPU? So ETH Analyzer is a wonderful tool that's available in Nexus that could be used to identify what type of packets are getting punted to CPU. So ETH Analyzer is an inbuilt packet sniffer. So you don't need any external sniffers, but this is an internal sniffer. It's simple command, ETH Analyzer command, which could be used to define the number of packets that you want to look or you want to filter it. There are quite a few filters available. So it basically tried to capture the packet and just display about what type of packets are received or sent by the CPU. So one difference here is the packets which are hardware switched will not be captured using ETH Analyzer. So it's only the CPU punted packet. So of course our primary intention is to see what type of packet is getting punted to CPU. So this tool, inbuilt tool comes handy. It could be used to identify what packets are getting punted to CPU. Excuse me. So in this example, like I said, we could use different filters to just filter what type of packet are we interested in. So ETH Analyzer also understands the protocol numbers. So if, for example, in this case, it knows that the protocol number is PIM, and if it is a PIM, it also knows what type of packet is it. So if it doesn't know, it simply will mark it as IP unknown. In this case, this is a actual multicast stream, so it doesn't understand what type of traffic is it, so it says IP unknown. But in this case, it understands that this is a PIM, and it also understands this is a hello or a join prone. So ETH Analyzer is not only about displaying and just, capturing and displaying in a hexadecimal value, rather it's a more user-friendly and the display is more reasonable. So reading our mrib, whoever is troubleshooting multicast, this would be the very first command that you will be executing. Okay, show IP mroad. Now, there are quite a few different details that are available. So this is just to highlight about what is it and how do we interpret these outputs. So the first one is, the IGMP is here. So basically, the IGMP here marks that these are the egress interfaces on which I have received the IGMP membership report. So basically, that says we have a directly connected, receivers on these VLANs, on these SVIs. So on SVI 501 and 500, we have directly connected receivers who sent IGMP join to us or IGMP membership report to us. PIM. This is an example which says, on this interface, I received a PIM join. So we have a PIM neighbor here and not a directly connected receiver here. So we have a downstream PIM switch, which basically sent me a PIM join for this group. So these two would help to identify if it is a IGMP triggered entry or a PIM triggered entry. So this PIM, the PIM at the top basically says that, the creation of this SG or star G also triggered the PIM join. So basically, this switch was able to identify the upstream interface and send a PIM join on our interface, which is VLAN 500. And MRIP, this is simply something which says that I've copied all the entries outgoing interface from star G to SG entries. Okay, so if you look into this, this is not a truncated output. So when you execute show IP mroute, in a traditional iOS, you would have noticed, there are quite a few flags which says, is it a shared tree or a shortest tree or different other flags like RPT prune set. So with Nexus OS, we don't have these outputs. Now that doesn't mean that we don't have those flags. It actually are moved to the relevant locations. So show forwarding multicast route, which is the mfib output from different line cards, we have these outputs. And the other flags which are relevant to the components like IGMP or PIM, they were moved to the PIM or the relevant client components. So show IP PIM route, you can see that the RP bit set. So if we send a prune with RP bit set for a particular start G, we could see all these entries here. So those flags are moved to the relevant components. Okay, so another commonly seen issue, or at least when we talk to different customers, the other commonly seen issue was when you execute show IP mroute, you might be seeing some entries in the pending state. So in the past, we saw that we create the state entry on mrib, and then we talk to different components. We talk to MFDM, MFDM talks to mfib, and mfib talks to the ASIC to populate the forwarding, so that the packet will be able to forward at the ASIC level. Now, once we have this, it also sends a confirmation saying, okay, everything is fine. So if the mrib does not receive a confirmation, or till it receives a confirmation, it basically will be marking it as pending. So basically, what it says is, the state entries are created on the mrib component, but it is not yet programmed in the hardware level. So if you look into the ASIC or the line card, hardware programming forwarding entries, you may not see the entry for the star G. So it basically says that I haven't got a confirmation saying everything is programmed fine on the hardware. So if you see it momentarily, it's fine. If you see it maybe for a second or two, it's fine, because it has to do a lot of work. The different components comes into picture, and they have to create those state entries on different components, and then program the line card. So if you see it for a couple of minutes, then it's fine. But if you execute show IP mroute for 5 minutes or 10 minutes and still you see it, then probably there is some problem. It basically says that one other component along the way is not actually doing its job. So let's look into each of those stages. So let's start from the client itself. So any of the state entries basically gets triggered either by IGMP or PIM, of course. I either need to receive a IGMP join or I need to receive a PIM join, so that I can first create a state entry, which in turn will be created on the mrib. So the very first thing is to look into the client tables. So show IP PIM route. Unlike the traditional iOS or other boxes where we don't have any specific routes for these components, the Nexus OS also have entries for PIM and IGMP. So when you execute show IP PIM route, you could see the SG or star G entries created by PIM joins based on the PIM joins that we receive. So this is an example of show IP IGMP route where we create state entries based on IGMP joins. So if you look into this table and you see the relevant outputs that you are expecting, then it simply says that the client protocols are working fine and they were able to create the state entries. Once we have that, of course, the next thing is to look into the show IP mroute to ensure that we have the start-G state entries or the SG state entries. And when we have the mrib state entries, the next thing to look into is the MFDM, because MRib talks to MFDM, and MFDM is the one that talks to mfib components. So the next step, once we verify mrib, is go to MFDM component and see if everything is fine. So this is the command show forwarding distribution. Again, this component resides within the supervisor. So you look into different components to see if you have that relevant start-G or the SG created on this output. If you don't see that, then that says that mrib is fine, but the communication between mrib and MFDM is not fine. There's some problem here. If you see those entries here, then the next thing to look into is the mfib. So mfib, like I said, is on a per module basis. For each line card, we'll have a mfib module running. So when you execute this command show forwarding IP multicast route, you will see that entry on a per module basis or a per line card basis. So we need to ensure that we see the state entries on all the line cards. Though our primary focus is on the ingress and the egress line card, it's also better to ensure that everything is on all the line cards we have those state entries. So if we have mfib entries, then of course it basically differs depending on the platform. The next step is to look into the hardware ASICs. Do we have all those state entries created? So if you, till this point, if you see all those state entries are fine, you see all those SG or the start-G entry created, then just engage a TAC engineer. He'll be able to further look into each of those, the met entries or the indexes or even the line cards. Again, it basically differs depending on different line cards. So they'll be able to help you with further troubleshooting. So this is like prelim and simple way of validating if each of those components are actually doing their job fine. So this is a consolidated cheat sheet which basically shows the different show commands on a per module basis. So like I mentioned, it starts from here. The client protocol talks to mrib, mrib talks to MFDM, MFDM talks to mfib or IPfib, and from mfib, it talks to line card. So this is a consolidated show command which helps you with the outputs from different modules or different components. Okay, so let's look into some of the troubleshooting specific to the VPC environment. So in this example, I'm just trying to explain what if we have a receiver which is connected to VPC environment and it's not actually receiving the data traffic. So while the problem symptoms I mentioned is like not receiving a traffic, the set of outputs that we have included here basically will also help you understand if you're also receiving duplicate data. So in VPC environment, we saw that we have different VPC peers, and one of the peers is supposed to forward the traffic. So I can see a couple of issues. What if both the VPC peers are not forwarding? Or what if both the VPC peers are forwarding? So in the former, the receiver will not receive any data traffic at all. But at the latter, they will be receiving duplicate packets. In either of these cases, it is an issue. So let's look into each of the states. So like I mentioned, we saw all along our presentation, I keep reiterating this because that's how even I learned it. So the moment when we receive a join, the very first thing that the VPC peer does is populate the snooping table and then create the start-G state entries, use the CFS message to exchange the information between the peers. So in this case, in our example, the IJMP join reaches peer 2. So on switch 2, we can see that when you execute show IP IJMP snooping, we should see the state entries. So the very first thing is to ensure that the client protocol has created the start-G state entry. Once you see this, the snooping entry, and then to create the client protocols table. So see if the start-G entry is created on the IJMP route. If you have this, then the start-G entry needs to be created on the mrib. So that's the next step. Once the client protocol table is fine, we look into mrib. So on mdiv show IP mroute, you could see that start G is created, which is created by IGMP, and the egress interface is VLAN 143. Now, the next step here is switch 2, it creates the state entries. It uses CFS message to synchronize the information with switch 1. So we need to look into the event histories, IGMP snooping event history, to see if peer 2 sent a CFS message to peer 1 about the snooping table. So this is the example where it says sent IGMP snooping message from switch 2 to switch 1. And on switch 1, when you look into it, you can see that it has received it. So the SI basically includes the port channel, the virtual port channel information, which could be used to synchronize the state entries between the peers. If you don't see this, it is a problem. It's not an expected behavior. If you see this, then it says that the peer 2 has done its job well, because peer 2 has to create the state entries and to synchronize the state entry with peer 1. So looking into this event history, we can see that it not only created the state entry, but it also sending the relevant CFS message to synchronize the information with peer 1. So once we see this information, peer 1 should have the data synchronized. So now if you look into peer 1's IGMP snooping table or IGMP route or IP mroute, we should have all these information created. So like I said, for start G, they both will have the outgoing interface list populated, and they will try to build the tree. So that's expected. So here, both VPC peers will try to build the tree. So when you execute show IP mroute, it's expected to see incoming interface populated, and the outgoing interface with the relevant VPC SVA is populated. Now, what is important here is when we receive the data traffic, when we start receiving the data traffic, like I said, we create the SG state entry and we negotiate the active forwarder. So for each source, we should see an active forwarder. So this is the command on peer 1 and peer 2. When you execute show IP PIM internal VPC RPF, for each source, you should see the forwarding state. So the forwarding state will basically says who's actually forwarding or who's the actual active forwarder and who's the non-active forwarder. So normally the forwarding state will be either a win-lose or it could be a tie. There's another one which we'll be seeing now. But win-lose is when they have different metrics. So imagine peer 1 has a metric of 10 and peer 2 has a metric of 100. Then in this case, peer 1 will be win and peer 2 will be lose. Tie says that they both have the same metric. So what if they both have the same metric? So that we still need a way to ensure that we don't see packet duplication. So when the metric is same, they both are tie because they have the same metric. So whoever's the active, whoever's the VPC primary role will be marked as the forwarder. So this way we still ensure that the packet does not get duplicated to the receiver. Okay, so in this case, our peer 1, because of its role, has become active forwarder, and peer 2 has lost its election. So peer 2 will remove the SVI from its outgoing interface list. So when you execute show IP mroute for this SG, as you could see, Nexus 1, because switch 1, because it's the active forwarder, will have the outgoing interface list populated, wherein switch 2, because it's not the active forwarder, will have the outgoing interface list as count 0. So again, like our friend asked, if there is a different L3 interface on which we received IGMP join or PIM join, it's expected to see here. That doesn't mean that something is goofed up here. It still is working fine. Is it clear? Okay, so this is the event history. So I was mentioning that we use CFS messages to exchange the metric and to basically identify the active forwarder. So this is the event history. So show IP PIM event history VPC on switch 1 and switch 2 will show that they sent with a different metric for each sources and who's the winner and why they won. Okay, so this is another example where we have source connected to the VPC peers, and imagine if the receivers are not actually receiving the traffic. So source starts sending the traffic. Like we saw earlier, the packet goes to one of the member, and the peer receives the packet. It creates the SG state entry. Excuse me. They both will create the SG state entry, but one of the node will be registering the source with the rendezvous point, and that would be the PIM designated router. So show IP PIM, when you execute, it's expected to see the SG state entry created, and the outgoing interface list is 0 because the source is actually connected to the VPC, and there is not any PIM join or IGMP join from any of the devices yet. So this is expected to, this is the fundamental multicast behavior. So as long as you're not receiving any joins, it's expected that the outgoing interface list will be 0. Now let's imagine, so in this case, this is another important thing. So the moment when we create a SG state entry, we saw that we exchange the CFS message, and we also, try to identify who should be the forwarder. So in this case, when they negotiate the source, they identify that the source is actually connected through the VPC peer. So you'll see win force here, and they both will be, in forwarding state. So why do we need both of these devices in forwarding state? And if they are in forwarding state, who would be the one that will be, forwarding the traffic to? So though the registration will be done by one of the node, which is the PIM designated router, they both will be in forwarding state. Why? It depends on, who's actually joining as a receiver. So imagine we have a different L3 interface which actually is, joining to receive the traffic. So no matter what, who's actually receiving the PIM join, they will populate the outgoing interface list and, will start sending the traffic to. So this is an example where I simply showed that, switch 1 does not receive any PIM join, but switch 2 received a PIM join from one of the downstream switch. So switch 2 will have outgoing interface list populated, but switch 1 does not have. Now imagine there is another receiver connected through a different layer 3 interface to switch 1. In this case, when it receives a PIM join, it's expected to see outgoing interface here. So it's a traditional multicast behavior, but from a source point of view, because the source is actually connected to the VPC peer, we make the source as win force, and both the nodes will be acting as a forwarder, and 2, whoever is actually receiving the data from the VPC node, the member link, they forward the traffic over the peer link so that both the VPC peers are receiving the data stream. Okay, so this is one not so commonly seen scenario, but still a very interesting scenario. So here we have a VPC peer where on one of the VLAN we have the source, and on another VLAN we have the receiver. So how do we ensure that the packet does not get duplicated? I mean, they both will be in win force. So traditionally, when we have a receiver, one of the node will be elected as the active forwarder, right? But when the source is connected to VPC peer, when you execute show IP PIM, RPF for VPC, you could see that both VPC peers are in win force and both will be in forwarding state. So how do we ensure that the packet does not get duplicated to the receiver? Show IP en route, when we receive the PIM join from a VLAN receiver, of course, for a moment, let's forget that there is a source. So it follows the same behavior. They snoop the table, they synchronize the table using CFS, they forward the IGMP, so they can both create the start G, and for start G, they both will be having the forwarding, the VLAN as forwarding. So all these things are similar. So they create the state entries with VLAN 13 on which we have the receivers populated as in the outgoing interface list. Now, the moment when it starts receiving the traffic goes to peer, and it follows the same thing. It floods the traffic over the peer link, but because of its MREB or the forwarding entry, it also will forward this from peer 2 when it receives it from VLAN 12 over this VPC peer. It replicate forward through VPC peer to the receiver in VLAN 13. So VLAN 13 has already received the data traffic from peer 2. Now let's look into how peer 1 is not actually flooding it. So peer 1 receives the data traffic from the peer link. So because it is actually receiving the traffic from peer link, not from any other member link, because it is receiving from a peer link, it follows the traditional VPC's loop avoidance mechanism. So when it receives it from the VPC peer link, it will not forward it again to the VPC ports. So if there is an orphan port, it will flood it. So this way, imagine there is another VLAN 13 which is connected to this peer, but it's an orphan port. I'm sure you might be aware of orphan port, right, which is not part of VPC. So in this case, the hardware is programmed in a way that it will not be flooding back to the VPC port, but only to the orphan ports or any other layer 3 interfaces. So, yes?
If the upstream switches would be connected on VPC as well,
okay.
They would be blocked as well.
That would what?
Blocked.
No, it will not be. Because no, so the loop avoidance mechanism will stop it only to flood it back to the VPC ports. But if you have a different layer 3 interface, it doesn't stop that. So even though you receive it, because it has received the PIM join, because a node will not send PIM join to 2 different upstream interfaces. It always will send only one PIM join to one upstream interface, right? So if this node receives a PIM join from one of the downstream interface, that ensures that this guy does not send PIM join to my VPC peer, but it's sent only to me. So this way, yeah, go ahead. Okay, this one, okay. Yeah. This one? Yes. This one? Yeah. Mm-hmm. Good question. So one thing, they both are not in same VLANs. So the source is in VLAN 12 and the receiver is at VLAN 13. So snooping is to ensure that at the layer 2 switch, when I receive the traffic, I simply will flood it only to the ports that belongs to the same VLAN, which has intended receiver. But there is a feature called MVR. I don't know if you're aware of it. Multicast VLAN registration, which basically is to address something similar. So MVR is actually not applicable for VPC environment, but MVR is basically like if you have a layer 2 switch, and if there are multiple receivers span across different VLANs, rather than sending the traffic all the way up to the PIM router and then receive it back on different interfaces and flood it, MVR basically will have additional snooping behavior, which basically will help us to do inter-VLAN flooding at the layer 2. But that concept is not applicable for this. So to answer your question, even though they both are connected to the same L2 switch here, they belongs to different VLANs. And so, though it snoops the entries here, it actually will be on a per VLAN basis. So this will not, basically create any duplication. Does that answer your question? Yeah. Okay. So again, these are some of the set of commands which are specific to VPC. Showtext or event history and other component-related commands, which will be very handy in case of troubleshooting. So whoever is actually from operational teams, this commands probably will be very helpful for you. That's all right. Okay, so this is an example, a basic example about troubleshooting multicast in VXLAN environment. So again, to reiterate, VXLAN or multicast in VXLAN, it's supported using ASM, but SSM or other bidirectional mode is currently not supported. So like I mentioned earlier, for each VNI, there should be a unique multicast address that needs to be assigned. So show NVE VNI will basically list us about the different multicast groups that are assigned for different VNIs. So if you have a bump traffic, or I'm just going with an example. So if the complaint is about, or the problem is that the bump traffic is not actually working between different layer 2 sites, identify the site first and the associated VNI. Execute this command to get the associated multicast group, and then check if you have the relevant state entries, if this multicast group was built as we saw so far. So show IP mroute, see if we have the start J entry. So there are two things. On any VTub, there will be a minimum of 2 entries created. One is start G entry, which will be built towards the rendezvous point, and another one is a SG entry, where the source is its own NVE's loopback address or NVE's source address. So why? The start G entry is used to receive the bump traffic from other sites, and the SG entry is used to send the bump traffic. So whatever bump traffic that I'm receiving on my directly connected L2 site, I use this SG, my own source SG to flood the bump traffic to all other remote VTEPs. So when you execute show IP mroute, you should see a minimum of start G and SG. And you can have more SGs depending on different VTEPs who are actually sending the bump traffic. So imagine if there is a remote VTEPs who's flooding the bump traffic. When you receive it, it's expected that you create SG state entry and then build the shortest tree towards the remote VTEP. So if the stream is not received, the first and foremost thing at least I would do was go to the ingress VTEP and execute this command, show IP mroute, the multicast group for the VNI, and the source address, which is the NVE's source address. So when you execute this, the very important thing here to note is the VXLAN encapsulation flag must be set. So this is a flag which basically says this is something that differs from the traditional ASM, because this basically says that when I receive a bump traffic, I'm going to encapsulate with VXLAN and then encapsulate with IP, setting the destination address to 239 and source address as 10.1.3.3 and forward the traffic. So if you don't see this VXLAN encap flag set, then that's something unexpected. That's not an expected behavior on an ingress VTEP. So the same thing goes true with the egress. So if the bump traffic is not working, so you log into the VTEP, which is directly connected to the layer 2 site where the bump traffic originates, and you execute show IP mroute and you see the entry, then that says that, okay, this guy is actually trying to flood it fine. Let's now go to the remote site to see if we see this show IP mroute. If you don't see that SG entry at all, then that says that there's somewhere along the path there's some issue. So follow the traditional troubleshooting that we discussed earlier. But if you see the SG entry on the egress VTEP, ensure that the VXLAN decap flag is set. So VXLAN encap flag must be set on the ingress, and VXLAN decap flag should be set on the egress. So this basically says that, okay, if I receive any traffic on this, it's not just a multicast, but it's something that is encapsulated with VXLAN. So I need to decapsulate the VXLAN and then perform a lookup in the relevant table. So this basically uses a combination of 239 and also the VXLAN header to identify the tenant to which the L2 bump traffic belongs to, and then perform a lookup in the relevant VLAN forwarding layer 2 multicast forwarding table and flood it towards the sites. Again, ETH analyzer is very useful here. VXLAN is a UDP based, so we will have VXLAN encapsulated, and on top of it, we'll have UDP encapsulated, and then we'll have IP address. So the port number, the destination port number on UDP is 4789, which basically says that this is a VXLAN packet. So if by using Ether channel, you want to specifically capture any of the VXLAN packets, though it's not applicable only for multicast. If you want to capture the multicast VXLAN, then use a combination of IP destination with the relevant group and the UDP port with the 4789. Because it's very handy, particularly when we are troubleshooting, we get a lot of packets to identify the right packet if we are really receiving it or not. This is very handy. So these are the traditional, the join and the prune messages. It's not much different from how it used to be earlier. Okay, so recommended reading. So in the acknowledgement section, I have even acknowledged one of my colleague and friend, Richard Fur. He, along with other my good friends like Vineet Jain and Brad, they have co-authored this book, which covers a lot of Nexus troubleshooting. So a couple of topic also includes multicast related troubleshooting, and they have done a pretty good job and extensively including all those different scenarios and troubleshooting. So this would be a very good book to read if you're primarily from the operations team and your day-to-day responsibilities is more like troubleshooting. So this would be a very good tool. So if you have any questions, the presentation does not stop here. Of course, you might be aware. So we have a Spark room, and I'll try to be as much as active as possible. So even if I don't have an immediate answer, I'll try to discuss with the relevant people within Cisco, and I'll try to get the response for you guys. So try to post any questions that you have, or even if you have any questions, feel free to ask me. Yes. Mm-hmm. 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 You're right. SG, state entry. Yes. Yes. Active forwarder. Yes. Yeah, so I don't know if you got a chance to look into that, but there are two ways of doing it. So the basic intention is to avoid loop or packet duplication between the packet duplication from the VPC peer to the receiver. So that's why one of the node will be active forwarder. The other one will stop building the tree. But with pre-built SPT, we still will be able to build it, receive the traffic, and drop it. So at any point in time, one of the node will be forwarding. If the active forwarder fails, the other one take over and forward the traffic. Till that, it won't forward the traffic at all. So like I said, it's still possible that we receive the traffic and drop it, but it's basically a trade-off. Because you'll be receiving the traffic for all the SGs all along the way from the source, and you do nothing. On the non-active forwarder, you receive it and keep dropping it as long as you don't have any outgoing interfaces. But the moment when the active forwarder dies, immediately you take over the charge, you mark all the VPCs as forwarding and start flooding the traffic. It depends. So it basically depends about how fast you can detect the failure. So using BFD, it's very rapid. Within a few milliseconds, less than a second, you obviously will be able to detect it. So depending on the volume of traffic, there definitely will be some packet loss, but it will be very negligible. Any other questions? Oh, okay. All right, so please fill in your evaluation form, particularly if you also want to add any other topics to this, or if you're interested in, because in the interest of time, because it's a 2-hour session, we try to be specific about what are commonly seen and what are commonly deployed in data center, but there are more, like fabric path-based multicast, or even in VXLAN, there are quite a few things. So in the interest of time, I try to consolidate as much as possible, which are relevant to a large crowd. So if you want to see anything more, feel free to use this and share your suggestions. So at least in next Cisco Live, we'll be able to modify it to accommodate all the things. So I mean, this is the last day of the event, so I'm sure you might be aware of all other, the WISP labs or the ILTs. So, I don't have to mention anything about this. So continue your education, and thank you.